So now we'll move on to another section. It's going to be a whirlwind tour of some interesting problems in statistical estimation. As with these other lectures, there's actually much more in the book. We expect you to read all of it, skim it all. Homework will cover other things. But we'll look at some of the big picture questions here, and we'll look at some interesting examples. So we'll start with the idea of parametric distribution estimation. So, and I mean, this is at the absolute core of statistics. So if you have, I mean, well, there's several. We won't look at the non-parametric case. We'll look at the parametric case. The parametric case is this: is that you have observed a variable, an outcome of a random variable, but you don't know which distribution it came from, and you have a parameterized set of distributions. So this is kind of the basic starting point in standard classical frequentist statistics. So this is the idea. So you have a parameterized family of distributions, and it's parameterized, the parameter we'll call x, okay? So yeah, this notation does not exactly conform to standard statistics notation. I guess it would be theta or something like this, right? But that's fine. Okay. Now, an absolutely standard method for estimating which distribution generated the actual observed outcome y is maximum likelihood estimation. And what that says is you take your observation, that's y, you plug this into the density. It doesn't, I mean, it can also be a discrete probability, but density, whatever you like, right here. And you consider this function as a function of the parameter that parameterizes the family of distributions, right? And that's called the likelihood function. And in fact, usually people take a log. It doesn't matter if you're maximizing. And so if you choose x by solving this problem, that's maximum likelihood estimation, right? So, and if you take a statistics course, you'll hear all about why this is a good idea and, you know, in some cases asymptotically optimal and all that kind of stuff. So this is L of x. That's going to be the log likelihood function. And you can add constraints on that. And a lot of times they're implicit. For example, x, the parameter, might include something like a covariance matrix, right? Because for example, your family might be Gaussians or something like that. And so the mean and covariance might be the parameter that characterizes it. And there, of course, the parameter that corresponds to the covariance obviously has to be positive definite, right? So these could be, then what you do is that's the domain of the likelihood function, and you would simply make one simple way is to simply say that this is 0 there, because then log of it is minus infinity, right? So, and that's infinitely bad if you're maximizing, right? So that's one. Okay, now, the maximum likelihood estimation problem, that's convex if the log likelihood is concave. But this is, by the way, this is different from a log concave distribution, which we've looked at before. This is log concave in the parameters that describe the family of distributions. Now, if you know about exponential families, then these two coincide because it's actually only they're both involve an exp of an inner product and then a normalizing constant. So if you know what I'm talking about, fine. If you don't worry about it. Okay? But it's a different concept. The concept here is the log likelihood function concave in the parameters that describe the distribution. Actually, something very interesting is going to happen. In a lot of cases, you'll sort of have what you think are the natural parameters for a distribution. And sure enough, it'll be log concave in those parameters. Well, we're going to see examples very shortly, right? But actually, in other cases, something really cool is going to happen. You'll look at the log concave, you'll look at the log likelihood function as a function of what you thought were the natural parameters. And guess what? Won't be concave. It just won't be. Here's an example. Let's estimate the mean and covariance of a Gaussian that generated a sample. What could be simpler? Okay? Well, it turns out the log likelihood function in sigma and mu is not concave. But it's going to turn out you just do a change of variables and it will be. Now, if you have had enough machine learning and statistics, you'll understand that it will not be a shock to you that the correct parameters there are like sigma inverse and sigma inverse mu. Okay? These are actually more natural, right, than sigma and mu. So again, this is a bit more advanced than I want to be at this point, but just to mention it to those people who know about these things, right? And it turns out those are precisely the parameters in an exponential model. So, okay. Okay. So, oh, and I should say that all of this material, our goal here is just to go over some interesting things. If you've never seen this stuff before, some of the stuff we're going to talk about is going to be super simple and completely accessible. But if you've had, some PhD level course in statistics or machine learning, then there'll be a little bit added stuff. And I'm going to mention some of that stuff like I just did, some of the more advanced stuff just for fun. Okay. So let's start with a very simple setup. Let's do linear measurement modeling. So here, x is a vector of unknown parameters, and we have linear measurements. So we have yi it's a scalar, it's a linear function of x plus a noise, right? And so, and by the way, this is a good point to stop and talk about sort of just, it doesn't make any difference at all, but sort of the philosophical way you would regard the setup, right? So if you're in something like signal processing or something like that, you would say, this says, your view of the world is, this gives you the ideal measurement if your measurements were perfect. They're not perfect. And VI is sort of like an added noise, right? So this is your corrupted or real or whatever you like to call it measurement, okay? And that would be the view from someone who does signal processing or something like that, right? That if you were to do something like get a perfect sensor and run this experiment at 0 or 0.01 degree Kelvin, right? So there's no thermal noise or whatever else that comes from, then in fact you'd get yi equals ai transpose x, right? Since you don't do those things, VI is a noise, right? So a statistician would say the following. They would look at that and they would say, y comes from a distribution, right? It's a distribution because that's a random variable right there, the VI. Those are random variables. They would say, so y comes from a distribution. And you say, well, what distribution does it come from? And the answer is, well, it depends on what x is. So x here is a parameter that tells you which distribution generated y, right? So I don't know if this is making, at the end of the day, you end up doing the same things with this, but it is actually just interesting to sit for a minute and think about the different views of what y equals ax plus v can mean. Okay, so there's nothing deep in this. I'm just saying these are the two views. Okay, now, what you do here is y has, and I'm going to assume that the VI are IID here with some density P of z. If x has the value x, or if the parameter has the value x, then the distribution, the density of y is this, right? It's the product because they're independent, and yi minus ai transpose x is, well, that's exactly VI, right? So, and then that's the value that VI had, and you simply take the product of the densities because it's independent to get the density of y, the vector, right? So that's the idea. By the way, other people would call something like this the residual, and the residual here is in fact nothing but the noise, right? So that's another way to think of this. Okay, so the maximum likelihood solution says here, if you want to estimate x by maximum likelihood, what you do is we'll maximize the log of this product, but that's the sum, right? And this gives you a hint as to why the log is going to come up often, right? So you maximize the sum of the log of the density of the residual, okay? Now, by the way, if the residuals have a density that is sort of centered around 0, right? And it'd be kind of, if they don't, by the way, that means it's sort of a known offset and it's a bit silly, right? But if they do, what that says is, these are functions that are kind of centered, this function is sort of centered around 0, and then it kind of goes off, right? It's a concave function that tails off after that. That's actually quite interesting because this is actually a penalty. This is penalty approximation, right? This is exactly minimizing a sum of a function which we previously called penalties. It's a penalty approximation method. But here the penalty is specifically the negative log likelihood if you convert this to a minimization problem. Everybody got this? So in other words, where you might just say that's the penalty and then give a story about your penalty function in terms of how much it irritates you to have a big residual, a small residual, medium-sized residual, all this kind of stuff, a negative versus a positive residual, that would be your discussion of why you're using a certain penalty. It says that all of that can be transposed perfectly to a statistics framework. And there, instead of saying something like, it irritates me to have a positive residual is more irritating than a negative residual, what you're really saying is something about the distribution the density of the noise. Okay? So let's look at some examples. Here's one. Suppose those noises are Gaussian. Well, then, if I take the negative log likelihood, I get this, right? So that's the log likelihood. And it's this. That's a constant. And when I'm maximizing over x, it doesn't matter. Here, this constant is totally irrelevant. And I'm maximizing this thing. Well, there's a negative sign there, so I can just minimize this thing. That doesn't matter because it's a positive constant. And so I minimize, hey, that's just least squares. Okay? So now you know least squares is nothing but it is exactly maximum likelihood estimation under the assumption that the noises are Gaussian. If you say you have a square and you say, what does that mean? You say, well, it means if a residual is small, I mean, it's fine with me because it's sort of small squared, but if it's big, that's not so good. What this says is that corresponds exactly to a statistical model with Gaussian noise. Because if you have Gaussian noise, and you say, well, if something's less than like 1 sigma or something, you'd say, fine, okay, nope, that's entirely plausible, right? Whereas if something were like 6 sigma or 8 sigma, you'd look at that and you'd say, that's I mean, I can't say it's impossible, but it seems very strange that my fit here or my estimation is telling me that the parameter, that what I've observed was an 8 sigma event. Everybody see what I'm saying here? So, okay. Let's look at Laplacian noise. Now that's noise with a density that is a double-sided exponential, like that. And it's actually a little bit interesting to look at that distribution. Compared to a Gaussian, what can you say about the tails of a Laplacian distribution compared to Gaussian? Much heavier, right? Because this is like e to the minus, z squared. This is e to the minus z. Okay, so it's way bigger tails. What that says is that the likelihood of a big outlier is, well, I mean, it's going down, right? It's e to the minus z, but it's way bigger than for a Gaussian. Everybody following this? And then this is a bit of a weird thing here, right? You have that point there. And it even says that something like this. I mean, that's going to tell you that the probability of being a little bit off actually is substantially reduced from being right at 0. Everybody, and that comes now just from probability from that kink right there. Okay, so this turns into, guess what? L1. And it makes perfect sense because now if you look at L1, you get both of those things about what happens for large residuals and small residuals. For large residuals, L1 charges you linearly, whereas least squares charges you quadratically. So it's not like it's not like you expect to have large residuals, but you don't go nuts as you would if it was quadratic or worse, right? And then you focus on small things, small residuals, and this says it actually keeps up it keeps up the incentive to drive a residual to 0. Right? And you can see that exactly here, right? So it's actually kind of interesting that both of these could be you can interpret both, but it's just from an intuitive description of a penalty function, abstract penalty function, or from the implied probability distribution of the noise in a additive noise model. Let's do uniform noise, right? Well, if you have uniform noise, then the log likelihood function is, it's actually just constant. And it's a constant, doesn't matter what constant it is, actually provided you are consistent with the measurement, right? And so there you simply solve a feasibility problem. And there are multiple maximum likelihood solutions, and you simply choose one that satisfies this condition. And all of those are maximum likelihood estimates, right? By the way, their statistical properties would not all be equally good. So because the maximum likelihood has been used for maybe 100 years, something like that now, is most of that theory assumes things like that this log likelihood function has a unique maximum or something like that, roughly, right? So, and that's not the case here. Okay. Let me mention just one other thing. So here, what this says is that you can actually go backwards. You can start from probability distribution and find the penalty because you just take the negative log of the distribution. But you can also go backwards, right? So for example, if you discussed with someone in some fitting problem what they want, and it's determined that what they want is something that looks like this, that's quadratic, and then this rises steeply. I don't know how this would come up, but it would. You'd talk to them, and you'd say, what do you feel about underfitting? And they'd say, oh, that's bad. That is not good, right? And you'd say, how about if you underfit just a little bit? No, that is not good. And they'd say, but what about if you underfit a lot? And you say, look, because the data's got weird outliers and stuff like that, if I have to underfit on a couple of my points, so be it. I don't want to go nuts over it. Okay? And that discussion generates that. And then you'd say, what if you overfit? And you say, well, the fact is, if you overfit a little bit, it doesn't make any difference at all. And then you say, well, what about overfitting more? And then they'd say, then I don't know. So anyway, it doesn't matter. You end up with a story like this, right? We all know this now. You can translate a little of the story and description into this. Okay? What this says is the following. It says then if a statistician walks into the room and you say, what are you doing? And they don't want to hear a story about your feelings about overfitting and underfitting and things like that. They don't want to hear that. So what you say to them is you say, oh, excuse me, I'm doing maximum likelihood estimation, right? This implies a distribution. And the distribution is very simple. It's e to the minus this. Of course, you have to normalize it, but that's it. So you'd say to them, you say, I'm doing maximum likely estimation. And for this problem, we can even say what it is. How would you describe this distribution? Somebody describe it to me. I mean, in words. So it's some weird Frankenstein distribution. On the left, it's got some weird exponential, right? On the right, it's Gaussian. And in the middle, it's got some uniform phase. Now, they would think you were weird. But then you'd turn to the statistician and say, no, we've been doing this for years, and we know this it looks like this. Okay, everybody got this? So it's actually very interesting that you can justify these from different points of view, and you end up at the same conclusion. Okay, so all right. Now these things here, by the way, are things that are kind of obvious. These are things we talked about in approximation, linear approximation. They're in some ways they're penalty problems with an affine function. Ax minus b or something like that. I mean that's what this is. But actually, what's interesting is in maximum likelihood you end up with all sorts of interesting things where you do not end up with an affine function, a norm, or a penalty function of an affine function. And so these are actually quite interesting. So we'll look at a couple of these. So first is logistic regression. So this is a distribution actually so the outcomes are 0, 1, so it's Boolean outcomes. And the probability that you get a 1 is the logistic function. So it's e to the a transpose u plus b divided by 1 plus a transpose u plus b. And the probability that y equals 0 is 1 minus this, right? Which, of course, is 1 over 1 plus e to the a transpose u plus b. Okay? So that's the idea. Now here, the idea is that you are here. These are observable explanatory variables, right? So, I mean, I can tell you all sorts of things about them. This would be, let's say that a patient admitted in the hospital eventually develops sepsis. That's what we're looking at. Okay, so and then you here would be all sorts of medically relevant variables, right? Could be basic, all sorts of basic things, various scores given to them, various. Anyway, doesn't matter. That's a whole bunch of things like that. By the way, some of these could be Boolean too. That would be very often the case, right? So they'd be so-called categorical variables, right? And so a model like this, and this model is instantiated by fixing A and B, then gives you a model of the probability of someone developing sepsis, right, when they're admitted to the hospital, right? So that, because you just simply take their u, you evaluate this function, and if it is 0.05, that's good, and if it's 0.87, that's not good. Okay, so that's the idea. All right. So the estimation problem is to estimate these parameters a and b from observations, right? So that would be that's what we're going to do. So we're going to work out the log likelihood function, and then we're going to maximize it, right? And I guess it wouldn't be in this class if it didn't turn out to be concave. So that's okay. So let's take a look at that. So what we'll do is, so you've been given a bunch of observations, and basically what these are previous patients, right? Could be from the last year, from the region, doesn't matter. So you just get a whole bunch of data, okay? And the y's are just 0, 1, right? So I guess you'd call these maybe labels in machine learning. All right, so we'll just make it simple and reorder them so that all the ones that actually developed sepsis are first, that's k of them, and all the rest did not, right? Just for simplicity. Then the log likelihood function, well, it's very simple. It's simply you take this over the ones where y was 1, so that's these terms, right? And then for the case where y was 0, that's 1 minus this, which is exactly that. And so that's the log likelihood function, and it's a function of a and b. Okay? Well, if you work out what this is, well, you can see all sorts of bits. This is log of the probability of exp, but that's just this thing, right? And then you get minus, and then here, there's this thing on the bottom. You sum that over all of it. That's log sum exp. But we all recognize log sum exp as convex, and so now we do this in discipline convex programming or CVX style. We just walk from the inside of the expression tree out, and you say that's affine. By the way, you don't then say exp is convex. That would be a false move. You recognize log of 1 plus exp as log of e to the 0 plus e to the a transpose u plus bi. And you say log sum exp is convex, log sum exp of affine is convex, sum convex minus concave. Done. Everybody got this? Okay. So what this says is, if you have a bunch of data, you simply maximize this function here, and that will give you A and B. That'll give you parameters A and B, and now you have a model, and you have a model that will predict probabilities for new and unseen values of U instances, right? That's the idea. So this is, of course, extremely widely used. So, and depending on your background, and I can speak for my own. So if your background is, from sort of traditional EE type things with signal processing, you probably won't have seen this, which is sort of a pity, right? You've seen a lot of stuff involving linear things and stuff like that, but you probably won't have seen this. So, okay. So here's an example, but this is an example where you hardly need anything fancy, right? But just so we can draw it. So the example here has n equals 1. There's one explanatory feature. It's kind of dumb. So that's U. That's here. And it varies between 0 and 10. And what are plotted here are a bunch of samples, right? And so ignore this curve for the moment. We just take a look at it, and we'd say things like this. Look, it's kind of, you don't need anything fancy for U equals 1. You look at this and you say, yeah, look, if U is like 2 or, I don't know, 2 or 3, below 3, it's quite likely it's quite likely that the outcome y will be 0. But it is not 1 because look at this guy up here. Okay, it's not probability. It's not the probability that your 0 is not 1, right? Because there are exceptions. On the other hand, if you say if u is bigger than about 6, it's quite likely that the outcome is going to be 1. But it is absolutely not certain because look at that. Okay, so what this shows here is the logistic fit, right? And so, it certainly seems about right, and it has all the weight of statistics behind it, so it can be justified at great length. And so the use of this would go something like this. A new sample will come along, and U would be 2, and you would say, well, I think the probability is about 8% that it's 1, right? U comes along, it's 8, and you'd say it's about 94% now. And U will come along and it's 5, and you would say, I don't know. Okay? So we'll move to a completely different thing, which is actually just hypothesis testing. Actually, these are all related because, in fact, maximum likelihood estimation with a parameter that is continuous is something like hypothesis testing, right? Because you're testing one value of x versus another. And in fact, we're going to see that maximum likelihood is basically it's the thing that would win in a binary hypothesis test against any other value. But okay, so here it is. This is its absolutely most basic form. It goes like this. And it's the most basic form, actually, of, well, I guess, statistics. It's this. What you have is two hypotheses, that you have a variable that was generated either from one distribution. This is finite value. It's got n possible values. It's either generated from one distribution or another, period. That's it. So they can't get any more basic than this. I guess you could have like 2, something here, but okay. So you have 2 distributions, and you see a sample, and what you want to say is you want to say something intelligent about whether or not, which distribution it came from. That's it. That's the most basic one. Okay, and some things would be obvious here, right? That if one distribution, looked like this, 0.9, 0.100 or something like that, and the other looked like, 0.05, 0.05, 0.8 and 0.1, then, you could guess, right? If in fact what you observed was, say, this one, then you can say with absolute and total certainty that it was this distribution that generated it, right? If it turned out to be, if your observation was 1, capital X equals 1, you could say with very good confidence that in fact it was generated by the first distribution. Everybody see this, right? So, and in fact, the whole idea here is as the two distributions get closer together, this gets harder to do. Okay, and so now we're just going to look at what is a good and principled way to make this choice. Okay, so we're going to look at randomized detectors. So a randomized detector, that's a matrix. It's going to look like this. It's 2 by n. These are the outcomes here, over here. So we write the outcomes here, and then this is something like 1 and 2. And what it is that each column is going to tell you what you should do when the outcome is, if it's column 4, if the outcome is capital X equals 4, right? So if you look over here, you might have 0.9 and 0.1. That's pretty weird because what it says is something like this. It says when capital X equals 4, you should say, actually it's going to be a randomized detector. So you're going to say, with probability 0.9, you're going to say that it was generated from distribution 1, and probability 0.1, you're going to say it was generated from distribution 2. So we'll talk about why you might do this in a minute. Now, much more natural would be things like this, okay? And that says that if capital X equals 7, you simply say, well, it was outcome 2. It was distribution 2 that it came from, okay? So this is the idea. Why you would want these a randomized detector, we'll talk about in a minute. Actually, it's interesting. You can also think of it as a relaxation, right, of an estimator. Okay. And if all the elements are 0, 1, it's called a deterministic detector. So that's the idea. All right. So how do you choose that detector? Well, if you simply multiply, you take there's a detection matrix, and the detection matrix is you simply multiply T by P, you multiply T on the left by P and Q, and you get a 2 by 2 matrix. And the entries can be interpreted in a very, very interesting way. They're basically the probability of error. So this gives you, this is if P is the true distribution, Q is the true distribution, and then this tells you sort of the probability of selecting the correct one, right? So these entries tell you something about the probabilities here of being right, right? Being right means capital X came from distribution 1, and you announced that it came from distribution 1. And you can swap 1 with 2, and that's being right. Being wrong is the distribution came from, the sample came from distribution 1, but you announced that it was distribution 2, right? And these have names like, false positive and false negative. And, that means one of these things anyway, so that's the idea, right? So this is the, this is the idea. Okay, so PFP, that's the probability of selecting hypothesis 2 if X is generated by distribution 1, and that's a false positive. So you're saying it's from distribution 2, but in fact it was from distribution 1, and the false. And of course, what you'd like is you want both of these things to be 0. I mean, you want this matrix to be I, the identity, right? Oh, there's another name for this. I think some people call it a confusion matrix, I think. All right. So we basically have a multi-criterion formulation, right? Because what you would really like, oh, by the way, how would you make a false positive rate 0? That you can do. You never want to select hypothesis 2 if it was generated by what? Yeah, you just make everything negative. And then the great news there is that your false positive rate is as low as it can get, 0. Okay, so that's one. And so I mean, it's a real trade-off here, right? All right, so if we make this a bi-criterion problem, it just looks like this, right? It's a very, very simple one. And the natural thing to do is scalarize. So if you scalarize, right, this will give you the Pareto curve. Actually, it won't in this case. You'll see exactly what it does get you, because the Pareto curve in this case is piecewise linear, and it gives you vertices on it. So we'll see that in a minute. So you minimize this, but in fact, this is completely trivial to solve. For one thing, the whole problem splits across the columns of T, right? Because the constraints only involve to tell you that the columns have sum up to 1, right? And the objective is linear, so it's completely separable. So this thing splits, you can decide each one, and then it's completely trivial to work out what the answer is. And the answer is simply this. It's very interesting. It says, here lambda, remember, is actually, and lambda has a beautiful interpretation. Lambda is remember something that translates, I think it's the false positive, irritation at false positive versus irritation for false negative, right? So it's the exchange rate between the two things that you want small. That's the interpretation from duality or multi-criterion. So the answer turns out to be really simple. It's this. You get a deterministic detector, and you should choose one if P is bigger than lambda Q. And this is sometimes written this way, like that, right? And the other one is written, of course, this way. And then this is called a likelihood threshold test or likelihood ratio test, right? So you simply have a threshold. And so all you do now is you simply take one distribution and the other one. You take the ratio, and then all you're doing is you're setting a threshold. And then for any given threshold, you choose whichever one has the higher value or something like that, right? So, or you sort these and then choose those. Anyway, and then as you vary lambda here, the ratio, then what you're getting are a trade-off. You're trading off false positive, and false negative. Okay? So now another one you could do is minimax detector. That's very interesting. So minimax detector says, no, I care about false positive and false negative equally. Please minimize. In fact, this says please minimize probability of error. I want to minimize probability of error. Then you get this thing, and actually that's an honest LP, and the solution is generally not deterministic, right? It's generally something where the detector has entries that are not 0, 1, 1, 0. Okay, so let's look at an example. I mean, obviously you don't need all this heavy stuff for this kind of thing, right? So here's an example. Here's two distributions. I guess that's P and that's Q. And some things are obvious, right? If the outcome is 1, it looks like a pretty good bet that distribution P generated it. If the outcome is 3, it looks like a quite good bet, rather good bet, that the second distribution Q generated the data, right? Just looking at it. And let's see. If the outcome is 2 or 4, it's maybe less obvious, right, as to which one generated it, right? So here is the trade-off curve. So this trade-off curve, it's piecewise linear, and this is showing you these various. So this is the actual trade-off curve. These actually are the points you get from the likelihood ratio test, right? Well, I guess you get these two. Those are the two we talked about before, which is how can you get 0 false positives or something like that? So you get something like this. So you see the idea. Oh, by the way, this picture, when I think you turn it. I think you just flip it top to bottom. It's got a name called ROC, which is receiver operating characteristic. Now the minimax one is 4, right? This line here is the line of equal error, false positive and false negative, and it's right here, right? So that's the idea. So it's a bit strange. By the way, this is one of those cases where, well, as a big picture, we will, and we have talked about these, and we will talk about it more, where you want to solve a problem, and you end up doing something like a relaxation. Right. So if someone comes up to you and says, these are the two distributions. I want you to estimate, repeat it. What's going to happen repeatedly is you're going to see samples, outcomes, and I want you to guess which distribution it came from. And I want you to absolutely minimize being wrong. Right? Simple. You have to use the minimax detector. What's weird about it is you're not consistent, right? Because you'd say things like x equals 3, and you go, yeah, that came from outcome 1. Yeah. And then later they say x equals 3. You go, sorry, that came from distribution Q. I'm sorry, the first one came from distribution P, then Q. So you're not consistent. It's a non-deterministic detector, right? But that is actually the only way that you can actually minimize the probability of being wrong, right? So okay, so that's that. By the way, it's not very interesting with 2 distributions, right? This actually is already very interesting when I have, let's say, 10 distributions. They're bigger and things like that. It's already way interesting. And I should add something there. You can actually get really interesting problems. If I show you 10 distributions on, let's say, 1,000 outcomes or 10,000 outcomes, it's actually there, your confusion matrix, or I think we called it the detector matrix. What did we call it? Fine, the detection probability matrix or the confusion matrix. It's got a lot of entries in it, right? Like, for example, it's got 100, okay? And you can think of all sorts of interesting convex problems you could do. You could say things like, you'd say, you know what? I absolutely do not, the probability that you think that you say that you estimate it came from distribution 7 when it really came from distribution 6, that absolutely can't exceed 10%. Okay? Everyone understood what I just said? That's just simply a linear inequality on one entry in that matrix. You see what I'm saying, right? And you can go on and add all sorts of convex constraints and things like that. You'd say the probability of being wrong when the distribution is actually generated from distribution 3. I want the probability of being wrong to be no more than 10%. What would that be, what I just said? What kind of constraint on D would that be? That's it. That's nothing more, right? Yeah. Either the diagonal element is bigger than 0.9, that's just fine, or actually the sum of the off diagonals is less than the number. That's the same because they all add up to, yeah, okay. Everybody got this? So, by the way, a lot of these problems are not, I don't think, taught in standard statistics type things or machine learning. I mean, I think there is. They have a loss function for all of these things, and so on. But you can now do interesting things just because you know about linear programming, for example. Okay, so, okay. We're going to go to our last sample here of topics. It's actually a very interesting one. It's experiment design, right? So, and it's in a very specific setting. It's in the setting where you get a simple problem, but it's actually quite interesting. It's very good to know about, and it's extremely useful. So it's this. We're going to have M linear measurements. So I have a bunch of measurements. Yi is AI transpose X plus Wi. And what we're going to do is we're going to normalize things to have all these noises N0, 1, right? So, I mean, so for example, if the noise actually had a smaller variance or something like that, I would scale it up, and that would actually just I'd scale A and Y would scale and all that kind of stuff, right? So that's it. So all the noises are normalized to have variance 1, standard deviation 1. Okay. And so if you want to, I mean, we can talk about various things here. X is a parameter we want to estimate, Y is a measurement. And you should interpret the size of A now as something like a signal-to-noise ratio, right? Because if A is big, if A3 is big, that means that's a clean sensor measurement. If A3 is small, that's a crappy sensor measurement. Everybody got this, right? So because the bigger A3 is, the bigger this chunk is compared to the noise, which is on the order of 1. Okay, so norm of A being big is good. That's something like a signal-to-noise ratio. Okay. Now, if I estimate this, well, the least squares estimate is just that, right? It's just whatever it is, A transpose A inverse A transpose B, and that's this. And we write it this way. And what you see here is it's a sum of the outer products of the AIs, and then inverse times this sum. Okay, so that's simple enough. Okay, now the error, that's x hat minus x, is zero mean, and it has a covariance matrix, which is actually just this thing here. So that's the covariance matrix. Okay, and notice that this kind of makes sense, right? Because look at this. If that's a covariance matrix, so it's a positive semi-definite matrix. Actually positive definite matrix. What's interesting about it is this. If AI is bigger, this thing gets smaller. I mean, if they're all bigger, right? Because we'll just look at it. This matrix is monotone in the matrix sense in AI. I mean, that sounds weird, but you know what I mean. It means that if you were to double A7, that dyad contribution would be bigger in the matrix sense. This matrix would be bigger. And then when you take the inverse, that would switch and be smaller. So you'd get better estimation. Okay, so it all makes sense. Okay, and so for example, if you wanted to get a confidence ellipsoid, that would be related this way. It would be something like this. You'd have x hat. That's your estimate from here, and you'd select beta depending on the confidence level you want. Depending on some chi-squared distribution or something like that. That would give you the confidence level. And so experiment design says the following. So all of this is basic. Experiment design is the following problem. You can choose from a palette of measurements that are possible. In other words, you have something like P possible measurements here. They're going to be denoted V1 through VP. And you are allowed to choose a bunch, like for each M, you choose one of those, right? So, for example, you might say something like this. I want all my measurements to be V1. That's why. Why? Because it's the best sensor, okay? Something like that. Or you might say, I want to do this. I want to start with V1 and then V2. Then I'll do a V7. Then I'll come back with another V1. Then a V. Everybody following this? So this is what you have to choose. Okay. Now some things are kind of obvious here. For example, it's a sum of dyads, right? So it actually doesn't matter what order you do them in, right? And in fact, the only thing you really have to say here to specify an experiment design is to say I want to do 22 of experiment 1, 12 of experiment 2, 0 of experiment 3, and so on. And those integers have to add up to m, which is the total number of experiments you're going to do. Everybody got that? So, and you can imagine all sorts of variations where you add costs for the experiments in time or money or something like that. You can imagine all sorts of things, but we're going to stick with the simple one at first. Okay, so we end up with a problem that looks like this, and this is a good time for me to say something. It's a general thing that we can talk about, and it's fun. Okay, so you end up with a problem that looks like this. Choose a bunch of integers, m1 through mp. They add up to m. In fact, what you're really doing is you're allocating a set of m experiments across p possible experiments. So it's an allocation problem, but notice it's an integer allocation problem, okay? And you want to do that to minimize this covariance matrix. Now, of course, that's a vector optimization problem, right? Because it makes absolutely no sense to say minimize a covariance matrix, right? So it's Pareto optimal. And many ways to do that. You could scalarize, you could do all sorts of things, right? There's many ways to talk about minimizing a covariance matrix, right? So, or if you like, if you like things geometrically, find me the smallest confidence ellipsoid, right? By the way, there is no such thing. So you want to say something like this: find me a small confidence ellipsoid, and that's translated to mean find me a Pareto optimal one. So Pareto optimal in that sense means find me a choice of these m's so that the confidence ellipsoid you get, there's no smaller confidence ellipsoid that you could get by another allocation of experiments, right? That's what that means. Okay, so, but we all know that because that's what multi-criterion optimization is. Okay. Now the variables are a bunch of integers. That should be lighting up a big warning sign. So the amber light in your convex optimization conceptual center should be blinking when you hear integers. And in fact, this problem is difficult in general, right? I mean, that's the right thing to say whenever you see integers. Actually, in some cases, it's false, of course. There are plenty of integer problems which actually are solvable, but in general, they're not. Okay. So instead, what we're going to do is relaxed experiment design. So relaxed experiment design says this. What I'm going to do is I'm going to rewrite it this way. I'm going to work with the fractions of the experiments of each type I do. And so I'm going to work with a lambda, and I'll have 1 transpose lambda is 0. And if I added one more constraint, if I added simply this, m lambda is in Z, then this problem would be identical to that problem, right? This says that the lambdas are integer multiples of 1 over m. So if I added this constraint, this is identical to that one. And now, you want to see how convex relaxation is done? Everybody knows this now. You know what convex relaxation is, right? Watch very carefully. Convex relaxation is this. You write down an optimization problem. There are a few constraints that you don't know how to handle. Comment them out. That's what it is, okay? What are some common scalarizations? Well, you can minimize the log of the determinant. That's a concave increasing function, and therefore will produce a Pareto optimal point. You can take the trace, maximum eigenvalue, all sorts of crazy stuff. You can add all sorts of, constraints now to it. Sorry, for this thing. Okay, so, and these have names, right? So when you minimize the log determinant of the inverse, it's beautiful interpretation. That's exactly, you are minimizing the volume of the confidence ellipsoid, right? And you end up with this problem, which is convex, right? So you solve that. And then, depending on if you were successful in convincing someone that was more sophisticated to solve the relaxed problem, you're done. If you haven't, then you round and you hold up the optimal value of the relaxed problem as a lower bound. Okay. Let's take a look at that. I mean, I'm not going to go into the details here. I'm not going to argue everything about the dual, but it's actually quite interesting. So the dual problem of this can be massaged I should say a dual problem, and that means you have to allow me to do a few little manipulations before and a few after, but you get it into a form that looks like this. Maximizes log det W plus a constant which is totally irrelevant, subject to VK transpose W, VK less than or equal to 1. And this has a beautiful interpretation geometrically. It turns out this says, find me the minimum volume ellipsoid centered at the origin that includes all the test vectors. And it turns out that the Lagrange multipliers on these constraints are precisely the fractions, the optimal fractions that you should use, right? So it's beautiful. So you get this connection between an experiment design problem and a geometric problem, which is going to be our next topic, right? And so the picture is something like this. Well, this is the picture, right? The picture is this. We have 20 test vectors. That's the origin, and here's a bunch of things, tests you can do, potential tests, and here's a bunch, okay? And now I'm going to, before we even look at what the optimal design is, I'm going to ask you some questions about it. Okay, so let me ask you, please explain intuitively why you would never choose that experiment. Let's suppose that experiment number 11. Why would you not choose experiment 11? You can say, and don't say anything about convex optimization or log det or anything else. Just you tell me, why would you not choose that experiment? Well, what is this experiment here? It's basically, it gives it's the negative of that experiment, but it's about twice as big. So in other words, it's a completely equivalent measurement with 1/2 the noise, twice the signal to noise ratio, right? So if I give you a palette of 20 experiments you can carry out, one is basically a copy of another, but twice as bad, then why would you ever use it? You would not. Okay, so I'm just saying, all of this is kind of intuitive, right? You want to use experiments that are spread apart. Now, roughly speaking, you don't choose any of these because these, well, not quite, because they don't go up here, but these measurements here are kind of like those. I mean, there's a minus sign, but who cares? Actually, it goes away immediately when you form that dyad. The VK transpose goes away instantly. So what happens is you're not going to choose any of these because these sort of stand in for them and have higher signal noise ratio. And sure enough, look what it does. It picks the two which have kind of highest angle, the two measurements which are most independent, if you want to say that, or something like that, have the highest angle, and it concentrates at 50-50 on them. Okay? So, by the way, this stupid thing in R2, you don't need this, right? But if you're estimating 10 or 100 parameters, these things are not obvious at all, right? Not at all, right? If you have 1,000 possible experiments to do, and so on.